Okay, so welcome you all on the last day of the webinar series. So today we have again with us our beloved alumni Ismail Khokhawala,
Thanks, sir.
and he is going to give the idea of a core topic of chemical engineering interest, that is the design of distillation column. So he is going to give the guidelines on how to design the distillation column on the basis of industrial approach. So welcome again, Ismail.
Thanks a lot, sir.
Now I request Ismail to start with the session.
Hi, good morning, everyone. Thank you, sir, for inviting me again. So I know the distillation is a core topic for engineering and students mostly during the course of when they are doing their coursework in chemical engineering. Distillation is one of the favorites subject with students like to learn more about it. So today I decided to take a case study on the distillation itself. Now, basically here in distillation, this is the live example which I have faced in my previous job, where I have designed this distillation column. To be very honest with you, I'm not going to go into detail in the methods of distillation like FUG method or the McApthil method. But before doing that method, what is required by a process engineer, I am going to give you a brief overview and how a process engineer thinks on distillation column designing, because when a problem of distillation is given, there are many hidden things within the problem itself. So how to identify that problem, how to eliminate that problem, and how to overcome the issues over it. So after all these hurdles are being overcome, then the part of McApthil or refugee method comes, where the distillation column is designed. But before designing, what backend data is required, how every aspect of the distillation column is studied, I am going to cover today. So I'll just start my presentation. So today I'm not going to show you any empirical equations or any mathematical equations like I have in my last presentation. I have showed you in the for the heat transfer. So I will try to keep it very simple. So we'll make sure that and I'll go very slow. So there are a few things which you need to understand how the distillation column can go wrong. So I will cover that aspect as well. Can you see the screen presentation? Hello. Hello. Am I audible? Is my screen visible to everyone? Okay. Okay. Thanks, Ratnesh. Thanks. Okay. So let's start the case study for the distillation column. Remember, since it was my previous company, previous job, so I will be keeping some information confidential, as I will not be able to give you any name of the components. But right now, the name of the components is not that important for you guys. It's like I need to be ethical on my terms as well, because since I'm not working with that company, I cannot disclose the name of the compounds as well. So I will just keep it like impurities, product, raw material, the name. But the idea is to understand how the distillation column works. So yes, first let us understand what was the problem given to us. So initially, the feed which you are seeing in the first distillation column, it is coming from a reactor, where it is fed to the first distillation column. All the three columns are batch reactors. So when we designed the process on the initial data, what we had, we proposed a 3 distillation column, where the first cut from the first column was the low boiler impurities. After that, the second cut which comes, it is azeotrope of the product and water, which is fed to the second distillation column. The third cut is the raw material and the water, which is again recycled back to the reactor. And that the last cut is the residue, which is sent to the effluent treatment plant. So the second cut from this first distillation column, that is the product and the water azeotrope, is fed to the second distillation column, where a suitable entrainer is used, and the first cut is the azeotrope with the entrainer and the water, which comes out. It goes to a decanter. Aqueous is separated, and the entrainer is again recycled back to the second distillation column. The the aqueous is then fed to the third distillation column because it still contains around 12% of the product. The second column, second product is you can see it's an azeotrope between the entrainer and the product, because the entrainer itself forms an azeotrope with the entrainer itself. So it is again recycled back. So in the next batch of distillation, no fresh entrainer was used. And the the third cut was the product which was 98% pure material, which was used for the next reaction. Now the aqueous which comes is which contains 12% of the product, you cannot directly discharge into the effluent treatment plant because it contains high organic, and 12% product loss and no plant will afford it. So for that we have proposed a third distillation column where it was without any entrainer it was used, and the first cut was like product and water azeotrope, which was recycled back, as you can see that from the dotted lines, which was recycled back to the second distillation column. So in the feed in the second batch would be the fresh stream coming from the first column and the recycled stream coming from the third distillation column. And the last cut of the third distillation column was completely aqueous with hardly 0.5 gram of the product, so that was easily discharged into the effluent treatment plant. Of course, whenever you have an residue coming out, you need to understand the characteristic of what it is, like COD, BOD, the TDS, organic matter, and everything, because you need to understand what is the characteristic of the aqueous as well, because sometimes it may create a difficult situation in the effluent treatment plant, because the effluent treatment plant is a heart of any chemical unit, because if ETP plant gets stuck, then the entire plant needs to be shut down, because ETP cannot handle a particular effluent above a particular load. So we had proposed this system, the three batch distillation column, to the management. So now, but the irony of the product was such that you mix it with anything and it is going to form azeotrope. It was something like that. So means you mix it, it formed azeotrope with water. The product itself formed azeotrope with the raw material. The product formed azeotrope with the entrance. So we were really worried how this thing is going to separate out. So so the challenge was for us was that to design a batch distillation column to get a 98% pure product. So we had proposed for that a 3 batch distillation column, but because of the capex cost, because the product which we were making, the final product was not that valuable product. So investing for a three distillation column for a single intermediate was a bit difficult to digest by the management. So it was we were not given that capex, and we were asked to develop a process to convert this 3 batch distillation system into one batch distillation column to reduce the capex. So it was a bit difficult task for us. So we started now, since it was a task given to us, so we as a chemical engineer, process engineer, cannot say a no. So we just started the distillation column designing again. So what is the data required for a distillation column designing? First is the exact feed composition. The feed may will contain your raw materials unreacted, then the product, and some impurities. Now in my last session when you must have attended, I had specifically emphasized on the impurities and its impact on the any of the process. So today here I will also cover that how the impact of impurity can disrupt the entire process. Then the thermophysical properties, which I had covered in the last session. Then in distillation, whatever compounds are subjected to the as a feed. So individual level, for the individual compound, vapor pressure curve, vapor liquid equilibria, and the azeotropic data are the most important thing which you will require. So vapor pressure curve is basically for the pure material vapor VLE data. So if you have 5 compounds, so you will have approximately 5 by 4 20, approximately 20 VLE curves with one corresponding to each other. But you should also know before doing the VLE curve that what the curve which you are making experimentally, because is it relevant or no? Because if you make like a matrix chart, if there are A, B, C, D, E, 5 components, so 5 into 4, so there will be 12 VLE curve. But out of that, I think 50% of the curve will not be valid. For data generation, you can do it, but is it required? That is a question to be asked. And then whether these components which are subjected in the as a feed are forming an azeotrope with each other or no. So that is that you will come to know through the VLE curve only. Sometimes it's very simple that VLE curves data are easily available, but most of the time in industry you will face the compounds where you will not have a single data for it. So you need to generate even the thermophysical properties and the azeotropic data for the distillation column designing. So when we started the distillation column, this was the initial feed. So the feed was approximately 40%, the raw material was 18.5%, and water itself was 40.3%, and impurities were 1.25. Now water was deliberately added into the reaction to avoid the undue impurity formation. So water was deliberately added. So it was acting like an inert material over in the reaction. But when you see the composition, I have highlighted impurities in red as 1.25%. So the concern was what, since it was a less in composition, the interaction with other components were unknown. We didn't know how it is going to react with all the above threes. So apart from design and distillation column, it was our first priority to make sure that to understand the impurities impact on the components. So initially impurities were unknown for us, so uh, we did some few batch distillation lab experiments in the lab and came to know that impurities can be classified into two categories. One was the low boiler impurities and one was the high boiler impurities. So low boiler came as the first cut in the distillation column, and high boiler was the high boiling component which left as a residue at the bottom of the column, so which were not the area of concern for us. So when we started distilling the low boiler cut, the low boiler cut started coming out at a vapor temperature of 50 degrees Celsius. So, but our concern was that a lot of product was being lost in the first cut as well. So when even at reflux of 35, we kept a reflux ratio of 35 in the distillation column in the lab, still 2.5 to 3% of the product on 100% basis was lost in the first cut. Means it was this first cut was of no use. This was directly going to the incineration. So burning 3% of your product was a matter of concern for us. So and in whenever you design a distillation column, please make sure that anything above reflux ratio of 3, the management is not going to approve you. Because now just imagine a reflux ratio running at a reflux ratio of 35, means your reboiler and the condenser are to be 35 times more in designing capacity as compared to the distillation column. So your heat load, the cooling capacity, everything goes increasing and the capex loss increases. So it is not viable to run a distillation column above a refresh ratio of 3. In some cases, critical compounds, yes, refresh ratio of 5 can be approved. But yes, reflux ratio above 3 is the suitable for from economic point of view. But now why we did at reflux ratio 35? So because we needed to isolate the impurities as well, because a lot of amount of product was coming with the impurities at the lower reflux ratio. So the main concern was how to control this loss in the low boiler cut. And the high boiler, as I told you, that it doesn't interfere in the distillation column as it remains at the bottom of the column, and it was the complete residue with a lot of water, so it has to be incinerated because the organic component was high. and also the calorific value was more than 4,000. So it was directly incinerated. So now the challenge, rather than in the initial slide, I showed you the three challenges what we were facing, and now the fourth one was added to it, that how to reduce the product loss in the low boiler cut. It means loss of product in the low boiler cut was directly a yield loss to us, and no plant will have a 3% direct yield loss in any of the product. So because yield loss is directly associated with the cost of the product. So we again focused on impurities and how to avoid the loss of product in the impurity. So first of all, as I told you, that we didn't knew what was the impurities. So identification. In the last presentation, I showed you that there are methods like GC mass, NMR, which are used for impurity identification. Then, with the help of this method, we came to know what was the impurity. Then whether the vapor pressure curve of this impurities is available in the literature. If available in authentic literature, then it's fine, you can use it directly. But if it is not available in the literature, then you need to generate the vapor pressure curves and the VLE curves. VLE curves with respect to the product and the reactant. So now for impurity identification, how we isolated the impurity, because you cannot just send any random samples for impurity isolation, for sorry, impurity identification. So rather than performing the entire distillation batch, our focus was to completely isolate an impurity in the highest concentration form. So the method like GC mass and NMR can easily give us the what impurities we are having. So we performed a few batch distillation to have an idea on the low boiler cut. So we did only the distillation to take the first cut out. Then the distillation was stopped, because there's no point when you do, because the primary concern now was to isolation of these impurities, so that you avoid the loss of the product. So we did approximately 3 to 5 experimentation to know initially what is the exact temperature range of this impurities and the exact composition. So based on this 3 to 5 experiments, we came to an idea that approximately 2% of the cut was being coming out as a first cut, like low boiler cut. So we took a batch of 5,000 grams, and approximately 100 gram was the first cut. Now we cannot send this entire 100 gram for the impurity identification, because the 100 gram, it has impurity, it has product, it has water, it has raw material, everything itself. So what we further did, that for further isolation, this 100-gram cut which we were collecting in a single cut, we divided into another 8 to 10 equal quantities, like 8 to 10 sub cuts, we can say. So the first cut of 100 gram was divided into 8 to 10 sub cuts. So here we had an idea that what is the exact vapor temperature of each sub cut, and what is the exact composition in each sub cut. So based on the analysis, the initial subcuts, the initial subcut, like the first, second, and the third subcuts, had the highest concentration of the high boiler impurities. So we used these cuts for impurity isolation, and using this method like GC mass and NMR, the impurities were identified. So what looks like the initial composition which I showed you on the top, now looks like it was bifurcated as impurity 1, impurity 2, and the high boiler impurity. So that 1.05 was split into impurity 1 and 2 and high boiler impurity. So high boiler impurity, as I told you in the beginning, that is was not a matter of concern, but now 0.42% and 0.216 were the matter of concern. So now we need to have an idea on how this impurity interacted with the product and the raw material, because we need to isolate it in the purest form, so that we can use the raw product in the further reactions, and the raw material which was recycled back. So now here when you see the system, the azeotropic data, so we were fortunate enough that both the impurities, impurity 1 and 2, were very common compounds. So azeotropic data and the vapor pressure curve was easily available in the literature. So impurity 1 and impurity 2 itself formed an azeotrope in the ratio of 12 is to 88 at a vapor temperature of 55, and data was available on the literature. So no azeotropic data was generated for these impurities. But impurity 1 was still left into the system, and it formed an whether it was forming an azeotrope with the product or no, we didn't knew it. So the composition was yet unknown, the temperature was not known, and there was no VLE curve. So we had to generate that VLE curve. Product and water was forming an azeotrope, but in literature there was just mentioned that the azeotropic composition of the product is in the range of 60 to 70%. That no exact composition was given there, and the temperature range was 90 to 100 degrees. And again, VLE curve was not available. Raw material with water, it was in the ratio of 51 to 49, and again the temperature range was 90 to 100, and again VLE was not available. Raw material and product, we had an initial idea that it is forming an azeotrope, but we didn't had any idea how, what composition, what temperature it is forming. And apart from this, there was another ternary azeotrope forming into the system with product, water, and the raw material. And again, no data was available for us. But when we did the initial study, we had an idea that this ternary azeotrope was forming at a higher temperature as compared to the binary azotropes. So again, this was a matter of least concern for us. Then the vapor pressure curve for, as you can see over here, for impurity 1 and 2, since it was easily available in literature, so we had the data. The data for water is easily available. We didn't have the vapor pressure curve for raw material products and high boiler impurities. So, and again, high boiler impurities, since we didn't have curve, we didn't bother to make it because it was not being participated in the distillation. So here you can see an equipment on the extreme right. This is basically complete a single glass equipment. Only the condenser is separable, but the entire equipment is a single glass equipment, and it is completely vacuum jacketed. Now this is the equipment which is being used to evaluate the vapor pressure curve and the VLE curves for the unknown compound. So I'll just explain you in brief how the vapor pressure curve and the VLE curves are being generated. Now, as you can see the bulb over here, you fill it approximately 90 to 95%. This is the heating element, which is basically electrical control heating. So basically, now for example, I'll just use an example of water. Now, if you know the temperature of water is 100 degrees Celsius, you keep the heating element at 130 degrees Celsius, 30 degrees higher. Now, since the heating will start, the vapors, you will see in this capillary, the small tube over this bulb, you will see that vapor and liquid will start traveling because of the capillary action. So once it starts traveling, it will go up, and here at the top of this bulb, there is a thermometer. You can place a thermometer where you can measure the vapor temperature of the vapor and liquid mixture. So there is an arrangement in this at the top of the system where liquid gets collected in one side and vapor passes through the holes in this and goes to the condenser and condense in this collector. This collector basically has a magnetic stirrer to it, so it keeps complete the mixture into the agitation. So once you have a constant temperature, you can withdraw the samples. You can withdraw the sample. So this sample over here from the sample which you collect below the condenser is basically hello. Yeah, hello. Can you see the presentation now? Hello. Hello. Is it visible? Okay. 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 So you want me to begin this again? This. Okay. You want me to begin this VLE curve again? Okay. Okay. Sure. Sure. Okay. So for example, now if you want to make VLE data for a binary mixture, basically, for example, if you have component A and B, so you have to prepare approximately 8 to 10 mixtures. For example, A is 10% and B is 90%. So this becomes your first sample. This is the first mixture. Then second is your 80-20 ratio. Like this, you go till A is 90% and B is 10%. So you have a range of mixture from 10% to 9% of A and B. So this is basically your feed mixtures. So basically this feed mixture you feed in this in this bulb and start heating. As I told you that heating the temperature should be approximately 30 degrees higher than your mixture temperature. So once you start heating, in this the tube over this bulb, it's quite narrow. The diameter is quite narrow. So because the capillary action, you can see the water, the liquid and the vapor going up in the upward direction. So once because of the pressure difference, once it starts going up in the top bulb, there is an arrangement to evaluate to check the temperature of the vapor and liquid, and there is an arrangement where the liquid again settles down here and it can be collected through this. There is a knob over here, so this becomes your liquid sample, and there is an arrangement inside the bulb where there are holes inside it where the vapor passes into this channel and goes through the condenser. It condenses and it falls back into the this collector. Now this collector has a magnetic stirrer where it keeps the mixture under the stirring. So once the temperature is constant, you can remove this sample. This is the liquid sample. This is the vapor sample. So you have an x and y point on the xy plot for this temperature range. Then you drain out this complete system and put another mixture like 20 and 80%. Same procedure is repeated till the temperature gets constant and the samples are withdrawn. Then it is drained and it goes up to the last mixture in the same manner. So make sure that when you get a temperature constant, remove the sample. At least the temperature should be constant for a couple of minutes, like 2 to 5 minutes. It should be constant. So once you get any deflection in 0.1, 0.2 degrees Celsius is acceptable. So once you have a constant temperature, you can easily draw the sample. So you have an x and y. X is your liquid sample and y is your vapor samples. So based on these samples, you can plot an xy curve. So this is how an atmospheric Whaley data is generated. Now, for example, if you need to generate a data under pressure, under vacuum, it's simple. The procedure remains same. Only there is an arrangement to be made that at the top of the condenser, you need to apply a vacuum. At what vacuum, specific vacuum, you need to generate the Whaley curve. So the entire method remains same. Only it is the application of vacuum at the top of the condenser. So you will use a four-way key and there is an arrangement where you can control the vacuum. There is one section of this four-way key is connected to your manometer or the pressure gauge, so you can control the pressure as well. So this is the usual procedure which we used to follow while generating the VLE curve. So I think I have generated more than 40 VLE curves, and I don't know, I would say more than 100 vapor pressure curves I have generated, because whatever compound we were facing, we were encountering, it was the compound which were not, the data was not easily available. And so this is how VLE curve is generated at atmospheric pressure or under vacuum. The only drawback of this equipment is that you cannot generate the VLE curve under pressure because it comes in the glass equipment, and it is single glass equipment, so it is quite delicate equipment. For vapor pressure curve, you have to follow the same procedure, but here you should make sure that whatever compound is being used for generating the vapor pressure curve, make sure that it is approximately minimum 98% pure, so you will get a proper vapor pressure curve. So again the method remains same. You fill this glass bulb with that pure compound, start hitting, it will start going up, and and usually with the when you are generating a vapor pressure curve, you will have to make a single mixture of the component, like sorry, single you have to take the single component. You don't have to change the mixture with every reading, because since you are using a pure compound, the only thing is that there will be a vacuum arrangement, and you will put a particular pressure, allow the temperature to get constant. Once the temperature get constant, note down the temperature and that pressure. Then with the help of the pressure control valve, again reduce the pressure, allow the mixture to heat again, to again get a constant temperature, vapor temperature. Once the temperature get constant, note down the reading. So you have the entire temperature range from 0 mmHg to 760 mmHg. So you will get an approximately a curve how you see in the literatures. So this is how a vapor pressure curve for a pure component is being generated with this equipment. So now when we knew what the compounds are, so then we later came to know that as we know, the impurity 1 and 2 were forming azeotropes. So VLE curve was not generated for that impurity. But since after the removal of this azeotrope, impurity 1 was forming azeotrope with the product in the ratio of 70:30 and the vapor temperature 64.5. So now we had a vapor pressure curve, VLE curve available for this as well. Product and water. So similarly, we generated for all the systems, all the binary azeotropes. We didn't bother to make a ternary azeotrope for this in this equipment, because that was something which was of least concern. So when you check the pure boiling point, impurity 1, 2 was 64.8, impurity 2 was 56, water, 100, raw material is 119, and product was at 114 degrees. So you can check that whatever azeotropes are forming are low boiling azeotrope. And now with the help of this equipment, we had the vapor pressure curves for all the components. So now what was our challenge? So apart from the first three, then the fourth one got added to reduce the loss of the product in low boiler cut, and the next target was given to us to improve the product yield. So now since we were knowing what was the impurities and how it was interacting with the system, so we need to control the loss of yield, the loss of product in the low boiler cut, as well as to improve the yield as well. So how are you going to control the loss of product and impurity? First of all, when you encounter when in such a distillation system where you are encountering 5, 6 binary isotopes, and one is a ternary isotope, don't get panic, because you consider every isotope individually. Forget about the other isotopes. Only consider the isotope which is a matter of concern now. So you know that our concern isotope was impurity 1 with product. So now you must have learned in distillation, in your distillation, that whenever you encounter an azeotrope, so to break an azeotrope, we use an entrainer, a suitable entrainer, I would say. But here there are again a criteria to choose an entrainer. Now, since we know that the boiling point of this azeotrope for the product and the impurity 1, we should make sure that we choose such an entrainer that it forms a low boiling azeotrope with the impurity 1 and not the product. Okay, so this was the first criteria in choosing the azeotrope. Then the second criteria was that you cannot use any random samples, any random solvent or a compound. First, try to use the say similar compounds which are used in the system as an entrainer. So so since this was a four-step reaction, and this distillation was a first-step reaction, there were one or two solvents being used in the entire system. So we first tried to use that solvents only as an entrainer to make sure that there is no extra inventory in the system. Because once you have an extra compound into the system, then again data generation is a task for it, because you know how the data generation is been required during the process designing. So if you have an known compound or a known solvent, then there is you are a bit in a comfortable situation. And okay, and but if these compounds which are commonly used are not serving the purpose, then obviously you will have to search for a third component, unknown third a new entrainer, so to avoid the losses. So in that situation, yes, you can try something completely a new compound, but whenever you have a system where there are solvents being used, try to use the same solvent as an entrainer. So it is just to avoid unnecessary inventories. So after a series of trial and error method, a suitable entrainer was found. And here I have not mentioned one more thing, that we required an entrainer such that it forms an heterogeneous isotope as well. So that was another criteria as well. So based on that, uh, a series of few trial and error distillation was done with different solvents, and a suitable entrainer was found, and we tried into the distillation column. So VALE curve with impurity was generated, as I told you, and vapor pressure curve was we had the data for vapor pressure curve. So based on this new entrainer, again this entrainer interaction of entrainer with the impurity was generated, and the vapor pressure curve was since the entrainer was a common compound again, the vapor pressure curve was generated from the literature. So now again the data look like the first azeotrope was quite easy. The second one was the which I marked in the red. The entrainer and the impurity one was forming an azeotrope at a ratio of 69 is to 31 at 63 degrees. And the literature was available. Since we had the equipment, we generated the VLE curve. So now the impurity one, the product, which was an azeotrope of a concern, was eliminated because the entire impurity got entrained out with this help of the entrainer, and the rest all the azeotrope remained same. So again, the here only addition is the entrainer temperature was 110 degrees Celsius, which we were using. And again, the vapor pressure curve, since the compound was common, entrainer was common compound, so the vapor pressure curve was available in the literature. So we didn't bother to generate the vapor pressure curve on the equipment. So how the challenge look like? So based on this intense permutation combination which we had done, so now and also the losses came down drastically when we used this entrainer as an azeotrope to form an azeotrope with the impurity. The loss that was approximately 3% dropped down to 0.025 percentage. So that was approximately from 3% to 0.025% was a big achievement for us, because that was completely going to accumulate in the yield of the system. So the yield loss was eliminated now, and the product yield was improved. So but still the initial challenge remained the same. So now why I'm focusing on this slide, because the second slide I showed you the challenge, but while solving this challenge we came across the two new problems. That is that what impurities were present, we identified, and what is the impact. And based on that, we came to know that approximately 3% was the product being lost on every batch. So that became the priority rather than designing a distillation column. So before designing, we need to make sure that no such losses were being incorporated. So based on this, we did some experiment, as I told you, and found an entrainer and made sure that the product loss in the with the impurities cut was reduced. So 3% was directly came down to 0.035. And moreover, the another advantage with this entrainer was that the reflux ratio which we are talking about was 35 dropped down to 1. So it was quite a comprehensive achievement by using this entrainment. So selecting an entrainment is also a bit of a task, because you need to know the interaction with the impurities, and you need to evaluate the its impact on the product as well. So now the question remained, the major target remains same: how to design a three-batch distillation column to a single batch distillation column. So what was required, that we had all the vapor liquid equilibrium curve, we had the vapor pressure curve, and by now we had all the thermophysical properties and of the individual compound and the mixture at the process temperature. So now we took some help from the aspen. So but we were so unlucky that the product and raw material was not the compound which was available in the aspen directory. So based on the above data, we generated the molecule inside the aspen model. We generated the model ourselves and made sure that the model was working properly, because when you generate a molecule in aspen, it will require the chemical structure, the molecular formulas, then two or three thermophysical properties, and based on your vapor pressure curve, and it will generate a vapor pressure curve with the regression mode. So once so how to evaluate that whether the model generated in the aspen by our physical data was correct or no. So the initial idea comes when you generate the vapor pressure curve in aspen. So you make sure that the vapor pressure curve generated by the aspen and the vapor pressure curve available with you, which you have done experimentally, should match. If it matches, it means that that the model is being made properly in aspen. So we were lucky enough that whatever data was available with us, the curve generated by aspen and the vle curve which we were having completely matched with each other. So based on that, we did some permutation combination in aspen, and came to a conclusion that if this distillation was carried out at a higher pressure, like 4 bar, it showed that there will be no single azeotrope. All azeotrope will break, and it can be done in the single batch column. So based on the aspen data, we tried to design this, but what were the advantages? That no additional entrainer is required. That means which we were using, which we found out for reducing the yield loss, because the product was being lost with the impurity one. So there will no additional entrainer required, and the fabrication cost is going to increase because you need to have a high thickness material. But again, the area was concerned that if you perform a distillation at a higher temperature, as you know, that as the temperature goes on increasing, as the pressure goes on increasing, the temperature is going to increase. So whether the compounds, that is the compounds of concern, was the raw material which was recycled, which is going to recycle back, and the product, are they thermally stable at that elevated temperatures? First of all, we'll have to evaluate the temperature at the particular pressure, that's the 4 bar. So whether the compound is stable enough at that high pressure or no. So again, it was unknown for us. So again, a new data was to be generated for this. So from the experimentation and the aspen data, we came to know that the impurity one, which was 64.8 degrees Celsius at 1 bar, the temperature rose to 98 degrees Celsius. Similarly, impurity 2 rose to 88 degrees Celsius. Water was at 100 degrees, so it went to 143 degrees Celsius. Now, product which was at 114 degrees Celsius, went to 168 degrees Celsius, and raw material from 119 to 178. So now maximum temperature means if you want raw material also to come out as pure at 4 bar, you need to make sure that your vapor temperature is 178, minimum one or maximum 178. If you require a vapor temperature of 178, means the temperature at the bottom of the reactor should be at least 15 degrees higher. So boiler you should make sure that your temperature is around 190 to 195 degrees Celsius. Then it will allow that the raw material to come out at 178 degrees Celsius as a vapor temperature. So now again, how are we going to heat the system? Either you use oil system, it's fine, it can work at atmospheric pressure. But if you use an high pressure steam like 10 bar steam, then again you require a jacket to handle that pressure. So it was becoming quite risky, but since we had a target to achieve this distillation in single distillation column, so for us it was again a matter of concern, a later part of the concern, that how this high pressure is going to impact on the fabrication designing. But first initial concern was whether this distillation is successful or no. So then we had to evaluate whether this product and the raw material are thermally stable at high temperatures. So now since we need to evaluate, since it was a high pressure system, you cannot use that glass equipment which I showed you. So you will basically require high pressure autoclave. So in that autoclave, you seal all the vents, charge your material of concern, heat the autoclave and keep it under stirring, attain the desired temperature and the pressure. And once you attain this, how you do a kinetics? It's just simple as that. Put your feed or a pure compound into the system, into the autoclave, attain the temperature and the pressure, and once it is done, once the temperature is attained, note down the time, and from that time every hour at the same similar condition draw a sample. Minimum time you should keep for 8 hours to have proper data generation. And if the distillation is critical, then make sure that it should that this experiment should run similar to the time required for the actual distillation. Means, for example, in plant, if you have designed a distillation column for example 14 hours, so make sure that this experiment runs for 14 hours, but usual time is 8 hours is sufficient enough. So now based on this experiment, the compounds might degrade or might not degrade. So we need to evaluate this. It's basically called as a degradation kinetics. So based on this data, we came to know that every hour the sample started degrading at higher temperatures. So we started with 98.63% pure material. It is an area by area analysis, and checked every hourly. So after 8 hours, the sample purity dropped down to 91.27%. So you can say that approximately 0.8 to 0.9% degradation was carried out. The product was degrading every hour. So now here you have to evaluate the equipment fabrication cost versus the degradation cost. Sometimes the degradation is quite less. So in that situation, you need to evaluate whether the equipment fabrication cost is more or the degradation cost is more. So, but here in this situation, degrading 8% of the product in 8 hours was not economically feasible. So this was completely unrealistic for us to design such system at a higher temperature. So based on this degradation study, the distillation under high pressure was not economically feasible, as the product was degrading at higher temperature, as you can see with this graph. So again, we came back to ground zero, that the 3-bed distillation column is feasible.
Ismail,
हाँ sir.
Sorry to interrupt you.
हाँ sir.
The left hand table जो तूने दिखाया है, that is A by what is area by area analysis?
area by area analysis है. इसमें वेट बाय वेट क्यों नहीं किया है? क्योंकि फैक्टर उसका 1 है, तो आप वेट बाय वेट करो, एरिया बाय एरिया करो, सब सेम रहने वाला है.
Okay.
So based on this data, So single batch distillation column was not a good idea. So again, we came back to the ground zero that we need to design a 3 batch distillation column. But again, because of the capex issue, we were knowing that it is not going to get approved. But this was the only solution where we can get a 98% pure. But when we had a meeting with the management, it was we didn't had approval to go ahead with this. So now, after evaluating all the data, when you know that single column is not feasible, practically it is not feasible. Okay, you see that 8% product is being degraded. So here the management will support you. Okay, don't go with this. But at the same time, they will also pressurize you that we don't want a 3 batch system, also 3 batch distillation column system as well. So now your target becomes quite difficult, because you know कि 3 batch में होगा but वो अप्रूव नहीं होगा, और सिंगल बैच में कर सकते हैं लेकिन प्रोडक्ट डिग्रेड होगा, which is not being approved by management. It's very obvious, but because people, because in industry they are not going to afford any losses like this, and losses like you saw in the beginning, 2.5 to 3% product was being lost in the first low boiler cut. So जब 2.5% 3% they were not allowing it to get into the incinerator. How the management is going to approve your design with 8% loss just to have a single distillation column? And also you should keep in mind that distillation column is a one time investment, and once, but that investment needs to be very clever. You cannot just randomly say okay, नहीं अभी one batch में नहीं, एक one batch distillation column में नहीं हो रहा, तो I will go for 3 batch only. So now, since there was a pressure from the management, so now it was as a part of a process engineer for us to think differently. So now, since it was an intermediate compound, it was not the final product, we really asked question to ourselves that do we really require 98% pure material? Is the purity that much concern? Or if can we have a lower purity material and go ahead with the reaction? Because okay, if you are doing a distillation and this is your final product which is going to be sellable in the market, then purity is concerned. But if it is an intermediate, then you definitely have to look from a different angle, that how this product is to be used. So now, as we know that in the first distillation column which I showed you, the azeotrope with product and water was 67 to 33. So we started asking question ourselves that is 98% the criteria for the next reaction, or can we use 67% product along with water azeotrope and go ahead? But if we have to do this, we need to make sure that the yield, conversion, and the purity of the second step is not compromised. Even costing should not increase, and the reaction time for the next step, which where the 98% pure material was going to be used, now you are going to use 67% pure material. You should make sure that the reaction time should also not increased. So all this criteria needs to be satisfied with this new purity material. So now the challenge become like this. The initially 3 steps remains as it is. Fourth and fifth we eliminated. So now the next challenge was that in the next reaction, if using 98% material can be replaced by 67% pure material. That was the first target. And the second one was that yield, conversion, purity is not disturbed. Means we should attain the same purity of the material as we are using 98% pure material. So now the focus from distillation shifted towards the next step reaction. So now process engineering was done for the next step to make sure that the distillation column sustained. So when we studied this next step reaction, we came to know that it was a condensation reaction. So usually condensation reaction as such that when two molecules combine together and a product is formed and a byproduct is formed, the mole to mole ratio is 1:1 for product and byproduct. So in this situation, we were lucky enough that water was the byproduct. So then we started thinking that when we have a 67% pure material with water itself, then why to eliminate water and get it 98%? Why can't we directly use this azeotrope into the reaction system and avoid the complete one distillation system? Because in the distillation column system which I showed you, the azeotrope with 67% pure material was fed to the second distillation column, and from that second distillation column we were getting a 98% pure material. So if this gets success with 67% pure material, then we can easily eliminate the second column. So based on that, we did some kinetic studies. As you know, as a process engineer, whenever you do any changes in the reaction, the first and foremost data required is the kinetic study. So we did the kinetic study data. At least 3 batches were repeated to make sure that we are getting authentic the data. So you have the data for the 3 different batches. Then based on that, we little bit scaled up the reaction and did the material balance to make sure that the conversion yield and purity was maintained as we were desiring it. Also again here, as impurity has an impact, so impurity formation was also studied, whether, because if we are using a lesser purity material, whether the impurities that were formed are increasing or decreasing. So that was also studied, and process engineering was done. And so a lot of process engineering was put in behind this reaction, because if this gets success, then the distillation scheme which we had designed can be come down to a one distillation system. So if this, so a lot of process engineering was involved in this system, in this second step reaction, where we are using a lower purity material as compared to 98% purity material. So now the only concern was that initial process you are using a 98% pure material. Now since you are using a 67% material along with which has a 33% water into it, the reactor volume is going to increase because of the excess volume by water. So how did we overcome this concern? So initially this was done with in a batch reaction. So we transformed this batch reaction into a semi-batch reaction, where where the reaction was carried out, and during the course of the reaction, the excess water was present in the system with the product, that is the azeotrope, plus the water formed during the reaction was removed with the help of the common entrainer. Now this entrainer and the entrainer used in the distillation column to avoid the loss of the product was same. So make sure that the entrainer you are using in the entire system, it should be single solvent method. So we use the same entrainer here and made sure that and the required catalyst was charged inside the reactor. So since it was a semi-batch reactor, so since it was a batch reactor and we transformed into a semi-batch reaction, apart from the limiting reactant, whatever was required, that is the other raw material, there's a 67% pure material, along with the entrainer and the required catalyst was charged inside the reactor. Then the reactor was heated to the desired temperature, and once the temperature was achieved, the limiting reactant was slowly at a controlled rate was added into the reaction system. So based on this, again 3 to 5 experiments were conducted at the lab scale, and by the end of the fifth reaction, when we did the analysis, we realized that the process yielded the required satisfactory result. Means there was no change in the conversion, there was no change in the yield, no increment in the impurities. So everything was under control by using this system as well. So later, to have a better idea from 1 or 2 kg which we do in the lab, we scaled up this reaction to a 25 kg batch reactor in the lab itself. So we had a better idea that how the system is going to work at a larger scale. So now the distillation system which I showed you at the beginning was changed into, means you can say that it was a combination, that the first step and the second step was combined together to make sure that every process work economically. So in the first distillation column, where you can see the feed from the second column was fed, the low boiler impurities using the entrainer came out without any product. The second cut, which was a product, an azeotrope with the water, was fed to this second step reactor, uh, to this reactor. Then the entrainer and the catalyst was added into it, and the limiting reactant was added once the temperature was attained. Once the temperature was attained, the water came out as a byproduct with the entrainer. It went to a decanter. Entrainer was again recycled back into the system, and the aqueous was again sent back to the third distillation column. So here you can see that second distillation column was eliminated. So based on this system, the third distillation column, as I told you, that it was again used to recycle back the product, because product and the water azeotrope, because it itself contained 12% of the product. So finally, this was a bit economically suggestion which management had to approve, because we combined the first and the second step to make sure that the system worked. And at present today, they have designed a commercial plant. I think from past 2 years they are using the same system into the commercial plants as well. So how we transformed? So the initial system was the distillation scheme which we proposed, but based on the data generated and VLE curves, vapor pressure data, the impurity profile, we changed the system to we tried to change the system. We generated the data based on Aspen modeling. It came down to one distillation column as well, but unfortunately the product and the raw material were degrading at higher temperature. So again, this idea of single distillation column was eliminated, and we again came back to ground zero. The three batch distillation was the only method, but then later, thinking differently, we came back, we changed the entire dynamics of the system, where we combined the distillation columns along with the second step reactor, and made sure that this process was economically feasible from product generation point of view. So this was the distillation scheme, and this was the proposed design which we proposed to the management, and finally it was approved, and today it is still working nicely in the commercial plant. So as a process engineer, as I told you that before generate using the methods like McApthil or refugee method or any other distillation method which you have studied, these are the hidden factors which you need to evaluate to understand the dynamics of the distillation column. Because as I keep on focusing, that the impurities that generate has a major impact. The entire impurity had changed the dynamics of the distillation column, because it was forming an azeotrope, breaking. So right from the forming of the azeotrope with the product, from breaking down the azeotrope using an entrainer, then make sure that that entrainer is common across the entire system, because you cannot have single every you cannot have a particular solvent for a particular process. So make sure. So from a process engineer point of view, you need to make sure that there is no more inventory cost added into the system, because the more compound is added, the more cost to the system. Then, as you know, that more solvents losses. So make sure that the solvents are chosen in such a way that it can serve the purpose of the entrainer as a solvent, and it can be used in multiple things. So based on this, we combined the first and the second step and made sure that the process go fine. And but the major task was that the yield. Now since we combined the first and second step together, we made sure that the first and the second step yield was not going down. Also, the impurities had didn't act funny, because when you change the course of the system, the impurities, you might found a new impurities. So you need to make sure that the impurities does not have the greater impact on your system. And also, now since in the beginning I showed you a low boiler and high boiler impurities. Now since we knew that a high boiler is not going to take participate in the reactor or the distillation, and is not going to involve, it is going to remain in as a residue inside the bottom of the distillation column. So we didn't had much data generation for the high boiler, because we know that it is not going to have participation in any of this thing. So no point in wasting your time and energy for such data generation which is not relevant. So make sure, because as a process engineer, you will not be given much time, like a final year project work के एक साल दिया project खत्म करना है. Sometimes you might give sometimes the management will give you few weeks, few days to generate the data and come to a conclusion. So you need to evaluate which data is more important. You need to evaluate what are the hidden parameters, like we came to know that impurities and bifurcation of impurities, impact of impurities on the product, data generation for it. So distillation column का design तो बाजू में ही रह गया. All this data start generating, and once you are done through all this thing, then the next step is whether to use a whether to use uh, uh, which method, means like McCapthil or FUG method or Ponchon solid, and then number of stages and everything has been decided. But this way you will be able to design satisfactorily, you can say 100% efficiently, once you have all this data in hand. So data generation for a process engineer is very important. As I told you कि अपने को सिर्फ as a process engineer सिर्फ samples निकालना है, but removing samples by during kinetics or during the generation of the VLE curve is very important. Make sure that you have a proper sample, because if you don't have a proper sample, if you don't do proper sampling, there is contamination. You are not going to get proper results. And if you don't have proper result, don't expect a proper designing things, designing equipment for yourself. So because these things really matter, because the sampling you do is hardly for 2 grams or 5 grams, but the data generated is for the commercial plant level. So make sure that the sampling is done very accurately. You should not repeat that you should not repeat the experiment again and again to make sure that what data is generated is correct or no. There is no self evaluation for yourself when you work in the industry. Make sure that the data is generated is authentic, and whenever you use it, you don't require to do an experimentation again to reconfirm whether the data generated was correct or not. Apart, if there are any changes into the system, then yes, then try some experiments, get a feel of the experiments, and then you can say, okay, this is required, this is not required. But yes, make sure data generation is 100%. I would say not 100%, 200% you should sure on your data. Then only this drastic change you can see on the screen that the complete, now the dynamics has changed. So this, the data generation, if your data generation is authentic, then you can have, you can have the guts to change the entire dynamics of the system. So the management will also get convinced with you, okay, that okay, we can go ahead with this, when because there is no yield loss, conversions are okay, purity is okay, and the impurities are not being that impacted on the product. So that's all from my side. If you have any questions, we can answer right now. Suraj sir.
Yes.
Sir. So any questions, we can try to answer right now.
Any questions can write in chat box.
Okay. So what is the capex cost? Can you explain? Capex cost is basically the hello. Can you hear me? Hello. So capex cost is basically capital expenditure. The full form, it is an abbreviation of capital expenditure. So before the start of the project, the management will decide that okay, you have a 40 crore capex approval for this project. So you need to make sure that you finish your process designing or the equipment designing or the plant designing within that stipulated cost only. So the capex cost is decided at the beginning of the process only. So you need to make sure that whatever you do working, it is within the capex cost. You cannot, okay, from 5% up and down, the capex cost can be tolerated. But if a capex cost is approved of 40, for example, 40 crores, So you cannot tell, okay, you require 60 crores. That is not process engineering. So you need to make sure that you achieve the target within the capex cost only. It is basically what company needs to put an investment behind a particular product based on its market value. Is it okay for you? Hello? So any more questions?
Hello.
Hello?
Students can ask the questions through chat box if any.
Yeah. So generation of VLE data, generation of the VLE data for ternary mixture is the same as I mentioned you in that way, how you do in the equipment curve, that the glass equipment. You make the mixtures of the known composition, like in binary, how we do 10% of component A and 90% component B. So these are what first sample, then you put. So similarly, in this system, hello.
Yes, yes.
So similarly for ternary, you need to have a ratio of the compound. Like you can have 10% of A, 10% of B, and 80% of C. Then you can increase 10, keeping 10% A constant, 20% of B, and 70% C. Then 10% A, 40% B, 50% of C. So based on that, you will generate a data. You will get a entire VAD curve. So process remains same at constant temperature. When you attain the constant vapor temperature, make sure that the samples are drawn accurately. What is the scope of reactive distillation? Yeah, reactive distillation is basically a process where you can relate this process to somewhere like reactive distillation, where a reaction is also carried out, and with the help of the entrainer, the water which is being generated is also coming out. So along with, so basically the condensation reaction can hello sir, बहुत disturbance. Hello.
Hello.
हेलो, आ रहा है मेरा आवाज, आ रहा है? कैन यू हियर मी? हेलो, हेलो. Yeah. So reactive distillation is something where you consider a batch reaction where only the reaction is being carried out. But when you have a system where a solvent or a byproduct which needs to be eliminated from the system, in this situation you can use a reactive distillation. Basically, now in condensation reaction, as I told you, that two molecules combined with each other forms a product and a byproduct. But here, the situation is such that if this byproduct, that is water, does not come out fast and it remains into the system, this byproduct can easily convert into the reversible reaction, and it will convert the product back into the into your reactants. So in such situation, you need to make sure that your byproduct, that is water, is distilled out the moment it is formed. So you don't allow the byproduct to remain into the system. So in this system, yes, you can use a reactive distillation as well. And also there are systems where during the course of the reaction you start distilling the solvents, excess solvents. So because in some situation, sometimes your reactant A and the reactant B, so one of the reactant is a solvent, so the solvent acts as a solvent also, and it acts as a reactant also. So in this situation, you, during the course of the reaction, as the product formation takes place, you have to start distilling your excess solvent as well. So in this situation, reactive distillants are being used. So any more questions? See, basically, degree of freedom is something, you need to evaluate what are the exact parameters into it. And basically, how we used to do a degree of freedom, we need to evaluate the, rather than degree of freedom, I would say we need to evaluate what are the important parameters. Because in in my complete my working career, we have never used this term degree of freedom. We basically use that what are the important parameters, what are the impact of that parameters going to happen to get an optimum conversion in the yield. And based on that, a particular system is designed, because you may have 4 or 5 different parameters which are going to work simultaneously on a system. But you need to evaluate that what parameter is going to have major impact on your system, which is, so you need to select the system in such a way that it should be a techno commercial feasible, means technology wise also, plus commercial wise it should not go out of cost. So you need to make sure, based on that process metrics, you need to evaluate that what is the important parameter you need to focus on. Because here as I told you that here as I told you that high boiler was not a matter of concern. So we didn't had any we didn't bother to generate enough data also on what are the high boilers, or what is the impact on it. Because we know primarily, even if we generate the data for this high boiler compound, it is not going to be part of the distillation system, because it is going to remain into the system. So we didn't bother to have a much idea or much data generation for the high boiler compound. So for a particular system, you need to evaluate, because as I told you that when you work in the industry, sometimes you will be given a few days or few weeks to complete the task. So you need to evaluate at a very faster rate that what is your area of concern. Because sometimes people tend to work in other direction and the area of concern is lost. So sometimes this process gets failed in this manner as well. So identifying the hidden data, or rather I would use the phrase that you should you should understand between the lines what is mentioned. So you need to evaluate what exactly the data is to be generated, and what is the impact of that parameter on your system. If we don't have access to lab experimentation, is there any further way to generate VLE data through simulation? See, now simulation, as I told you, uh, in Aspen, yeah, so when you use the word simulation, the first thing that comes into mind is simulation. Now, since Aspen was there with us, we didn't had this compound into a system. Aspen does not have either the raw material and the product. So you need to generate the VLE data anyhow by experimentation. Because see, Aspen is a simulating tool. Uske he is not the Aspen is itself is not going to evaluate the person's competency who is going to put the data into it. Because you are going to give some input, and based on that, whatever method you choose, it is going to throw some output. Whether that output is relevant or not, it's a job of a process engineer. So we should make sure that what data you feed to Aspen or for or any simulating software, you should make sure that, and that you have the relevant data. And similarly, VLE data Aspen generation for common compound is similar, but for critical compounds like the unknown compound, you have to have the lab VLE data uh, in hand. So even if you have one VLE data, you can generate with the help of the regression mode. You can generate VLE data for other pressures in Aspen. But yes, you will have to give input of VLE data. Now your concern is that if you don't have, I don't know whether my this method is correct or no, but this I have used it and I have never found this problem. So what you can do, generate the, for example, if there is a compound A and compound B, you can take like methanol and water. Now we know that it is not forming an azeotrope. Okay, so you have the VLE curve, assuming that methanol and water are an unknown compound which are not available in Aspen. So at least you can generate the vapor pressure curve. Even if you cannot generate the vapor pressure curve, with the help of in the literature, there are methods available to have an theoretical vapor pressure curve for a particular compound. There are methods available where you can generate a theoretical vapor pressure curve. So generate vapor pressure curve for compound A and compound B. Here, only one assumption you will have to keep in mind, that component A and component B does not form an azeotrope. So now based on this vapor pressure curve, you will come to know what is the low boiling compound, what is the high boiling compound. So high boiling compound, for example, if it's methanol, its vapor pressure is 760 mmHg at 64.8 degrees Celsius. The second compound is water. So what you can do, you know that at 64.8 degrees Celsius, methanol vapor pressure is 760 mmHg. Understand this very carefully. It's very simple, but understanding is very difficult. Vapor pressure of, with this vapor pressure curve, the 760 mmHg pressure at 64.8 degrees Celsius. Now try from the vapor pressure curve of the second component, that is water, that at 64.8 degrees Celsius, what will be the vapor pressure of the water? So you have two vapor pressures now. Divide it, you will get the value of alpha. And if you have the value of alpha, you can generate with the help of X, like how you do in this column, you can generate the VLE curve. But this is, I would like to say that there is nothing mentioned like this. This is based on my experience, I have done in my previous job, and I am telling you, and I have never faced problem. But yes, there is nothing written literature like this you can generate. But yes, you can get, but in this method, the only, as I told you, the assumption is that component A and component B will not form an azeotrope. That is the only basic assumption. So if this assumption goes correct and is not forming azeotrope, then this method may be viable for generating a VLE curve if you are in a tricky situation where VLE in the lab is not possible. So you can try this method, but I am very sure that if you have an Aspen simulation for common compounds, you can easily generate data from Aspen. But for non-common compounds where the data is not in the Aspen library, you will have a bit of a tough time. So you need to generate the data anyhow. Hello, any more questions? Any particular case study? Now, case study, see, basically, if you have some representative in the industry, you can take their problem and ask them what are the difficulties they are facing, and then do a case study that okay, you can, rather than doing this, you can use this methods as well. So this is, and I don't think in literature you will find some case studies so easily, because this data from the industry are confidential, at a confidential level, so sharing also becomes a bit difficult. So that's why, this is also the process where I have worked. That's why I have never mentioned any component's name, or except water. Impurities 1 and 2 were also very common compound which I have mentioned, but since I have to be ethically on my part, that I should not name any of the components. So if you have any contact with the industry, that you that, and they trust you, that okay, you are just using this as a case study, then you can use it. That's it, because you need, the company should able to give you that case study, because academics wise, or from this what you can say, in the syllabus you don't have anything like case study. But yes, you can, or if you want to work on a theoretical case studies where data where you are only concerned with data evaluation, then for example, like you can take for example, any heat exchanger problem, and make sure that uh, if you replace a double pipe silent tube heat exchanger by uh, graphite heat exchanger or spiral type heat exchanger. So what data will you will require to change over from double pipe from shell and tube heat exchanger to graphite type heat exchanger? What will the cost impact? So you can do a case study like this. Or I think there are, if you are really concerned for case study, then there are you can search on Google CSB safety videos. So there, they highlight some chemical reactions, the disaster which has taken place in the past, and they tried to do a case study over it and how it could have been eliminated, or like Bhopal gas tragedy. There is a complete, I think, 10-15 minutes video over it where the person who was in charge of the plant is explaining what happened and how it could have been eliminated. I also have that video with me. I will share it with Suryavanshi sir. So, sir, I will share you the video of the Bhopal gas tragedy. It is available on Google as well, but I will share you on WhatsApp so you can share with the group that the entire process was explained by a chemical engineer who was in the plant of the Bhopal gas tragedy the day the tragedy happened, and he explains the entire case study that how this could have been avoided. But since it was a government bounded industry, so nobody had bothered to listen to him, and he very well before the explosion or this disaster happened, he had predicted that this type of accident was going to happen in the plant. He had proposed a particular designing of the system, but nobody listened to him. And finally, on the 3rd December, this tragedy happened. And then later he takes as a case study and he has explained it completely that how it could have been avoided. So you can search CSB safety videos on YouTube. And this you can use as a case study for your college presentation or something like that as a theoretical work.
So any questions? Okay, Ismail.
Yes, sir.
I think no more questions on the topic.
Okay.
So, Ismail, once again, thank you for such a wonderful and informative session on distillation column design. This might be gives the idea to students how the design proceeds in which direction and how to start with any particular type of the design.
Yeah.
Thank you for giving such a informative information to the students.
Thanks a lot, sir. One more thing I would like to add, that why I specifically chose this case study, because when it comes to distillation, the first thing comes into our mind कि यार मैं कैप्सूल यूज कर लेंगे और कॉलम डिजाइन कर लेंगे, एफयूजी मेथड यूज कर लेंगे और डिजाइन हो जाएगा. But before designing of the distillation column, what are the hidden parameters you need to identify? You need to rectify your distillation column, because after every 3-4 slide I was changing the challenge slide, so everything was getting incorporated, something was eliminated, some more challenges were added. So before going to the distillation column, you should filter out what you need, what you don't need. So that was the prime focus. I know that based on the syllabus McCapsule method and you will learn FUG method and everything. Learning that method is good, but identification of problem is an art in the distillation column. Not only in distillation column, in any of the chemical equipment designing, identification of the hidden problems which are going to cause you a failure in the later stage is a disaster. So once you design a column and then you come to know, we didn't study this impurity thoroughly, now it is having impact. We are losing yield by 3% because the product is getting lost into the impurity. So now the column is fabricated. Now you cannot do anything. that is a complete loss. So that is not how a process engineer should work. So you should make sure that you get the highest yield at the optimum cost. So that was the prime focus, just to widen the thought of this young engineers, that how in the industry you should think.
This is no one is going to share such kind of information to anybody. Even from that, you have share your experience how to proceed with the design of any equipment related to chemical engineering. Thanks for this wonderful session.